Okay, so we are here to learn the method of integrating factors, which is a general method for solving linear ordinary differential equations. Okay, so how we're going to do this, the first thing you need to do is rewrite it into the form. And this is kind of a standard form for solving them, and I'll actually unpack this a little bit for you. U of t minus h of t, u of t equals g of t. All right. Another way to write this a little bit simpler without all the t's in here would be u prime minus hu equals g. And you just need to remember that hg could be functions. Okay, they're not just scalars. But you need to write it in this form. And a little bit of commentary here that's not tied to the method, which is that you should start to view, when it's written in this form, you should start to view this over here as kind of the system, and this over here is like the input signal in general. So this is a system or the output signal because it is, how the rate interacts with the quantity that's present. And on the right-hand side, this is what's telling you what's being fed into this system at time t. This is a generalization of this form. It, applies to many different ways of viewing. Sometimes, if it's just a purely mathematical equation, this doesn't make any sense. But from an engineering context or physical context, this is a good way to think about a DE written in this way. That you've got the system on the left and this input signal on the right. Okay. So once you've written it into this form, then you can apply this method. Again, the hope is that, hey, I hope this came out of the product rule, so why don't I write it as if it did? So we find the integrating factor. Now, the integrating factor, there's a bunch of ways to write this. I'm going to use some kind of informal notation. What it is it's e to the opposite of the integral of h of t dt in the exponent of e. Okay, so the antiderivative, you need that negative sign because you need to negate it, of whatever this is. Now, it can be any antiderivative, so you're just going to choose the one that is nicest, meaning it doesn't have a constant of integration. So that is what you choose to multiply both sides by. You can, change this around. You can call this h of t equal to this integral here, just to kind of make this a little bit nicer. We know, right? We can say, well, h prime is maybe little h of t. So that big H would be the antiderivative. And so, likewise, this is going to be our integrating factor. And we're going to use this just to kind of simplify the general process. But mostly, you're going to write it like this because that's the workable form of this thing. Okay. So this is the integrating factor. I mean, you multiply both sides by e to the minus h of t, u prime minus h times u equals g times e to the minus h of t. And again, the left-hand side, and you might take a moment to really unpack why this is the case. I showed it in the last video. But the left-hand side really looks like the derivative if I was taking the derivative of u times e to the minus h of t. Right? See why that's the case, knowing what the derivative of big H is, that negative sign, the product rule, etc. So that's the left-hand side, and this is equal to g of t times e to the minus big H of t. Then we will integrate both sides. Integrating both sides allows us to unlock this piece on the left where we've got u times e to the minus ht equals the antiderivative, and this is with respect to t here. Don't get sloppy, Mally. G times e to the negative big H of t dt. Again, remember we're going to have a constant of integration over here. And so now to solve for u, which again is our goal, we're looking for a function, u of t. We're going to multiply both sides by e to the positive h of t. As we saw last time, this will undo these negative exponents. All right, so let me scoot over here. So we've got you've got u times e to the negative h of t equals the integral of g of t times e to the minus h of t dt plus c. And so we multiply both sides by this e to the positive h of t to cancel out this term on the left. So we're just left with u of t equals e to the big H times this antiderivative plus and then c e to the big H of t. Okay, so notice how this got distributed on the left to both terms, this integral and this constant term. It's very, very important, actually. Another thing is that this can't really be distributed in because it's a function of time, so this kind of has to sit outside of this integral. All right. So, but this is the general form of the solution to every equation that are in the form that we started with. Okay, so we did this in general. So this will always work, and then you can obtain a particular solution to an initial value problem by just plugging in the initial condition and solving for c. Okay, but this is the general solution. It's like the double general solution because it works for all equations that satisfy these conditions. All right, so let's do a quick example to just show how this works again. I'll do it the long way and then the quick way. So first of all, what do? We write it in the form that we want, which is u prime minus that h u equals g. Notice that they're both constant coefficients here, or that we have a constant coefficient and the forcing term is constant. That's a better way to say that. All right, so we identified that, little h of t is 2. So that means negative big H would be 2t, right? It's the antiderivative of t. Let me just, in case we're feeling rusty, right? So we take that to be our big H of t. That should be negative. Please make a note of that. So then this is going to be our integrating factor then. It's e to the negative big H, which is e to the minus 2t. All right, so this is kind of our side work over here to identify that integrating factor, and now we can plug it back in. Well, not plug it in, but multiply both sides by e to the minus 2t equals 4e to the minus 2t on both sides. And then our next step was to write the left-hand side as the derivative of that mysterious function multiplied by the integrating factor. So, u e to the minus 2t equals 4e to the minus 2t. And now we integrate both sides. 4e to the minus 2t dt plus constant of integration. And then we multiply both sides by that e to the positive 2t to then get u by itself. And then we've got e to the 2t times 4e to the minus 2t dt plus c e to the 2t. All right, so we've kind of got these two distinct terms here. All right, please note that this one on the right is not inside the integral. Now, we can carry out that integral. Sometimes you can't, sometimes you have to leave it in an implicit form or indefinite form. That's okay, but, we obviously don't, that's not ideal. So, but we can do this because this is an easy integral inside. So I can pull out this 4, I've got 4e to the 2t times the antiderivative of e to the minus 2t is really just negative 1/2 e to the minus 2t. And so that's that piece plus c e to the 2t. And then the good part here is that we get to, cancel out these terms. So you got 4 over negative 2. So that leaves us with u of t equals negative 2 plus c e to the 2t. This is what? This is a general solution. And, if I had an initial condition, plug it in, solve for c to find that particular solution. So this is the long way following the full process. Now I want to show you how you can just kind of jump to the end after you do this a number of times. It's really important that you actually do it the long way first so that it just doesn't become this random formula you apply. This drives a lot of our other methods, which you do need to understand. So, but you'll see that if we just started with the equation, try number 2, shortcut way. And I'll even write in here, after you understand or after you do the full method 5 times. And I really hope you take my advice. So our equation was what? U prime equals u prime minus 2u equals 4. So then again, understanding your integrating factor term, that e to the minus h of t is e to the minus 2t. So then just using the formula that we saw at the end of the method, which is e to the big HT, so u of t equals e to the big HT, so positive e to the 2t times the integral of g times e to the minus ht, so g was 4 e to the minus h of t dt, plus c e to the h of t. And you see we're right back where we started, right? Or we're right back where we had the solution at the end of the last attempt. And you can carry this forward, yada yada. So you've got negative 2 plus c e to the 2t. So this will always work as long as your equation is of the form we discussed. Things obviously get complicated because we're talking about integration. So you throw in a factor of t or a factor of sine of t or something like this, it's going to be a very different integral. And so that's where these practice problems are going to help us work out these subtleties and how intricate these problems can get. But that's the general method with one example, and then how the shortcut applies at the end. But again, make sure that you really understand how to do this method from top to bottom before heading there. All right.